Hello, I'm Doug Montgomery, and I'm your instructor in our massively open online course on design of experiments, and I'm also your host for our Fireside Chat. And welcome back to the Fireside Chat if you've been here before. Um, I always want to run this Fireside Chat with a guest speaker so that we can talk about specific topics and that are of interest to people in the experimental design community and applications of some of the DOE concepts. We always have some time at the end of the guest presentation for Q&A. And this is a terrific time for you to ask questions. And they could either be about the content of the Coursera courses. It could be a question that's related to the guest's a topic, or it could be a question about a specific situation that you're encountering in your work life, and we'll be happy to try to answer those. For those that are on Coursera, we post these Fireside Chat recordings to the courses, and you can find them in the Resources tab of your course. Uh, Quick reminder, please keep your mics muted and your cameras off during the session so that we don't have any disturbance. I know that FDR, when he did his fireside chats, he always had his dog Fella there, but we don't need any barking dogs or crying children or anything like that. We have enough going on anyway. If you want to send in a question for either me or our guests, please do that using the chat function on the Zoom menu bar. And you don't need to wait until the Q&A starts to submit your question. You can start putting in the question at any time during the session. And if your question doesn't get answered during this time, we'll respond to it in Coursera if you're enrolled in the Coursera program. Uh, our guest today, I'm delighted to have as our guest today Bill Woodall. He's Professor Emeritus of Statistics at the Virginia Tech Department of Statistics. He's a former editor of the Journal of Quality Technology. This is in 2001, 2003. He's been an Associate Editor of Technometrics. He's the current editor of Quality Engineering. Bill has published 200 referee journal papers, most of them on various aspects of process monitoring. He's a recipient of the American Society for Quality Shewhart Medal, the ENBIS Box Medal, the William G. Hunter Award, the Jack Youden Prize 3 times, the ASQ Brumby Award twice, the Ellis Ott Foundation Award, the Soren Biscard Award, the Lloyd Nelson Award, and the IISE Transactions on Quality and Reliability Engineering Best Paper Award back in 1997. He's a fellow of the American Statistical Association, a fellow of the American Society for Quality, and elected member of the International Statistical Institute. I've been friends with Bill for a very long time, and I've worked with him on a number of projects. We've published some papers together that I'm very proud of, and I consider him truly one of the guiding lights of our field of industrial statistics, and I'm delighted to have him as a guest. So, Bill, uh, I'm going to turn this over to you. He's going to talk about a topic that I'm really interested in, and I think we need to get the word out on this. So, Bill, uh, the floor is yours.
Okay, thank you. I certainly appreciate the opportunity to give this presentation, and I appreciate everybody that is in the audience as well. Let me share my screen here. If this is going to be. Okay, I think that's got it there. Uh, I'm going to talk about Neutrosophic statistics, and you can tell from the title, I don't have a really very positive view of it. But I will give you an easy to use alternative approach instead of using Neutrosophic statistics. And I did want to point out at the beginning that if any paper that you're interested in that I mentioned, I'd be more than happy to send copies out there. Here's my email address, and I'm easy to find on the internet. Now, the first question is, what is Neutrosophic statistics? Well, the founder is Florentine Smarandaci, who I'll discuss a little bit more about him later. But he wrote in his book here a dozen years ago that Neutrosophic statistics is an extension of the classical statistics. And while in classical statistics, the data is known, formed by crisp numbers, in Neutrosophic statistics, the data has some indeterminacy. All right, crisp number is what we call in statistics just a number. The number 5.2, for example, single numbers. But in Neutrosophic statistics, we're not really sure about the number, and invariably they use intervals. So this is an example. Those of you that are interested in design of experiments, this is a row column design with 3 treatments, A, B, and C. But the most important thing to note about this is that each observation is an interval, and the interpretation of the interval is important. So I'll be talking about that. So we have interval data. That is the key here. And you might ask, well, when am I ever going to have interval data? Well, anytime you take a continuous measurement and round it, you have an interval. For example, if I round round weights to pounds, then I have an interval of length 1 pound. So, for example, 100 pounds would go from 99.5 to 100.5. Now, most of the time, the interval is so short that we can just use the midpoint and not worry about the fact that we have interval data. But sometimes the intervals are wider and we can't ignore them. Can happen when you have an excessive amount of rounding or when you're binning numbers. There's several different ways that you can end up with interval data. So typically we use midpoints. Now, some of you are familiar with Don Wheeler. He's written about this problem of having what he calls chunky data. Chunky data is just data that's been rounded excessively. So suppose, for example, we have weights in pounds, but what we really need are weights in ounces. So it's the data has been overly rounded. So he says that this can cause a problem, and he considers using the midpoints of the intervals a strategy we don't recommend. If you have wide intervals, it's not good to use the midpoints. Now, if we have interval data, anything calculated from the interval data gives you intervals, and the Neutrosophic ANOVA table for the data that I showed you a minute ago is given here. Some things to notice about this: if you look at the total Neutrosophic sum of squares, you'll see that the larger number is on the left instead of on the right. That doesn't really cause a problem in the Neutrosophic theory, although we would always put the smaller number on the left. The degrees of freedom are constants, and then we have intervals for the mean square, F statistic, and the p-value. So the key is, how do they get these numbers and what do they mean? And I'll be talking about this example in more detail. But before I do, I want to give some background. I think it's important to understand what's happening here with Neutrosophic statistics. Google AI says that there are over 4,000 publications related to Neutrosophic statistics and probability. And I have no idea how accurate this is, but if you go to Google Scholar and put in Neutrosophic statistics or Neutrosophic probability, you'll get an idea about how many papers are out there. There are a lot of them out there, and the number is growing. Now, the founder of Neutrosophic methods, Florentine Morindaci, he's retired from the Gallup campus of the University of New Mexico. He would be considered to be a hyper prolific author. If you look at what he wrote here, this was taken from ResearchGate, so this is what he wrote. He says he's published more than 900 papers, over 400 books on a wide variety of different topics. Certainly has wide-ranging interest. I'm focusing purely today on the statistics part of it. Now, on Google Scholar, I want to make a couple of points here. He lists Neutrosophic statistics first as his interest area, but Neutrosophic algebra, neutrosophic geometry. I think it's interesting to note and important to note that there are neutrosophic versions of virtually every area of mathematics, not just neutrosophic statistics. And this list of the various versions of neutrosophic probability statistics I have here on the right came from an email message that he sent out to many people, including me, when he was trying to solicit articles for an edited book. But there's certainly different ways of looking at probability and statistics. But I think that those of you that are familiar with probability and statistics would find that all these different topics are just a little bit maybe over the top. Now, let's look at some examples here. This is a very simple example from his book, Introduction to Neutrosophic Statistics. It's got 4 observations. We have 6, we have an interval from 2 to 5, we have 30, we have an interval from 18 to 24. Now, this is important because he explains here what the interval represents. He says that the interval 2 to 5 means a number in this interval, but we don't know which one. So there is a number, we're interested in the number, we know it has to be between these bounds. And although it's never stated, you don't want these intervals to be any wider than required. So I think it's reasonable to assume as well that every possible number is in here, and all the numbers in the interval would be possible numbers for this quantity that you're interested in. Now, just as a minor point, he wants to come up with a neutrosophic median. So he converts the 6 and the 30 to intervals. And then we know that to get the median, you average the middle 2 observations here. So he averages the interval 2 to 5 and 30 to 30. Some of you might realize that there's not really quite right. There's a step he's leaving out. I don't know, Doug, do you see it? When you're calculating the median, if you have an even number of observations, you're going to average the 2 middle numbers, but you have to, first of all, put them in order from smallest to largest, which he didn't do here. So really, he has an interval on the mid-range, not the median. And this is not one of my major criticisms of neutrosophic statistics, but it's just maybe, if anything, just a sign of what is to come. Now, I had never heard of neutrostatistics until 4 papers were retracted from scientific reports. And to retract a paper where the authors don't want their paper retracted, it's a pretty involved process. There has to be a post-publication review. Some qualified people have to review the papers. The author is always given the chance to respond to the questions and so forth. But it turned out that their replies were not considered sufficient. So you can read here that the mathematical arguments, a lack of clarity in the terms presented, and inferences that were not adequately justified. And I think this sort of summarizes the point I want to make during my talk today. And if anything, I think this is sort of watered down. Retraction statements tend to be watered down to some extent. Now, the other leader in neutrosophic statistics, Muhammad Aslam, he was an author on the 4 papers that were retracted. He had a short article in Retraction Watch where he referred to the reviewers as being irrelevant, and they were unable to understand the new area of statistics. So Muhammad Aslam, he's also a prolific author, publishes 50 papers a year. Now, this little short article appeared in Retraction Watch. And if you're interested in what's going on in the literature today in terms of various types of misbehavior, then I highly recommend that you look at retractionwatch.com. So, Muhammad, I'm going to refer to some other of his publications as we go along here. Now, Ann Driscoll at Virginia Tech and Doug and I are all interested in process monitoring. We noticed that there were dozens of papers on Neutrosophic statistical process monitoring in the literature. We reviewed these papers and we wrote sort of what our view was on it. And the main point that we made here was that they never explain how they do their calculations. None of the results that we saw were reproducible because they had formulas involving intervals, but there was never any explanation of the mathematics that was used. So that was one of our points that we made. Also, another point was they sometimes assume that the sample size is indeterminate. Even after you take your sample, have your sample in hand, which we didn't really understand that. So we had this. It's really, I guess it could be considered a critique. They came back almost immediately, Florentine Smarandacci and Muhammad Aslam, trying to respond to our points, but in our view, didn't really do an adequate job of answering our questions. I'm sure they're going to want equal time on Doug's Fireside chat after they see my presentation today. So anyway, we thought that was the end of it, but it actually didn't turn out that way. It is important to know that there is a field of numerical analysis called interval analysis, and it can become very, very complicated. But this is a major point here. A function of interval values could be data, but it could be other values as well. Is it interval itself? So the interval for the function contains all possible values of the function for all possible combinations of the input values within the interval. So interval analysis deals with looking at all possible combinations of the inputs that are consistent with the input intervals and trying to bound those, bound the function. So hopefully I'm getting myself a point across here, but you have interval valued inputs. For any combination of inputs that meet those restrictions, you're going to get a value of the function. Well, the interval for the function contains all those possible values. All right, so interval value, in some cases, you might be dealing with a theoretically infinite number of combinations here if you assume continuous intervals. But at any rate, you're going to have many, many, many different combinations. Well, we wanted to avoid getting into this complicated mathematics. So our approach was to use simulation. So we assumed a probability distribution for each data interval. We picked a uniform distribution, although we pointed out that you can pick any distribution you want. It turns out we got criticized for picking the uniform, but I can talk more about the effects of that in a minute. So we simulated many samples, 10,000. Sometimes we would check the results with 100,000 samples. Turns out that 10,000 samples is really easily enough. So we end up with thousands of samples of single value data. We can use standard statistical methods for each sample, and then we summarize the results. So it's a simplified way of trying to estimate in a way what you would get using interval analysis. All right, so I really want to make sure this is clear. I tried to explain this one other time during the presentation, and it seemed to be a little confusing. The thing is, it's so simple that I think people are sometimes expecting something more complicated. But if you look at each of these intervals here, there's 18 intervals. We're going to put a uniform distribution on each one of these intervals. And then I'm going to go, for each sample, I'm going to take one number at random from each of the intervals. And that will give me single value data. I run the ANOVA, I get a result. I do that over and over and over and over again and summarize the results. So once we came up with this idea, then we thought, well, now we can at least evaluate the Neutrosophic results to see how they compare to what we get with our simulation. And that's led us to this paper. Caleb King joined Ann and Doug and I on this paper in quality engineering. And what we found, again, for this example, This is the Neutrosophic results that I showed you before. The p-value going from 0.19 to 0.14. And this is, the histogram is for our simulation results. So it's very clear here that the Neutrosophic method does not bound the p-values. The p-value that you can get doesn't necessarily fall in the Neutrosophic interval. And again, that sort of violates their principle of having the interval contain all possible values. So you can fall outside the interval with the Neutrosophic approach. So again, we thought this was interesting. We had this published. We have other examples in our paper as well. But there's always seems to be a follow-up here. And the follow-up in this case was that my co-author, Abdul Haq from Pakistan, actually figured out how the Neutrosophic calculations were done. All right, so now we have additional information about this. And it's interesting. Keep in mind that the interval analysis approach that's in numerical analysis could have theoretically an infinite number of samples. We're looking at 10,000 or 100,000 possible samples. The Neutrosophic method looks at two samples. The two samples, one would include all the lower data limits, one would include all of the upper data limits. So they're only looking at two. And if you do that, this is their Neutrosophic ANOVA table. All the numbers on the left-hand side of these intervals come from using the lower data limits. All the numbers on the upper side come from using all the upper data limits. And that's how they get their results. So these p-values down here can correspond to those two particular samples. Now, once we publish this, there's always a retort from the Neutrosophic folks. So again, Muhammad Aslam, Florentine Smarandaci had a critical evaluation of the criticisms against Neutrosophic statistical methods. So really, this is a critique of our critique of their critique of our critique. We can say we're not really converging here. But this is what they wrote about that particular example. The p-value for the classical statistics is 0.194. But there's no justification for this. The p-value for 0.194 comes from using all the lower data limits. If anything, a classical statistician would use the midpoints, but there's no, I don't think anybody would use the lower limits in analyzing the data. The p-value for the indeterminate part, 0.138. All right, so this is important. This can be interpreted as suggesting that under uncertainty for this real data, the p-value may range from 0.19 to 0.14. All right, this statement violates what we show in our example. If you look at the plot, which they did when they wrote this reply, it's obviously not the case. They're not bounding the p-value. And so this statement that they have here is just flat wrong. So it's very difficult to argue with individuals that when you can't agree on the facts. So the fact here is that the Neutrosophic interval does not contain all of the possible p-values. And I've had a lot of correspondence back and forth with both Muhammad Aslam and Florentine Smarandaci and asking them, what is it that you're saying that the Neutrosophic interval is trying to capture? You have an interval, what are you trying to capture? And they could really never answer that question. And I think, if you can't answer that question, I don't think you have a meaningful interval. Now, an example, a simple counterexample showing that you can't just use the endpoints to bound a function Because if you have a single data interval, say going from -1 to 1, and we're looking at just x squared, if you apply x squared to the endpoints, then you just get 1, 1, which is the crisp number 1. But interval arithmetic and I would say common sense would give the interval from 0 to 1. Right, so the point being here is you can't just apply the functions to the endpoints. It's not that simple. If it were that simple, then we wouldn't have the field of interval analysis. Now, I just wanted to quickly go over this. This is not really something I want to go through in detail, but just as another example, this was a completely randomized design. The point I wanted to make here is that in this case, the Neutrosophic interval does a much poorer job. So sometimes the Neutrosophic interval is just way, 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 way off. Now, these are designing experiments examples. I wanted to cover one example in regression and also point out that there is an area of interval statistics. There's a literature on interval statistics in the classical statistics literature. Lynn Ballard at University of Georgia has done a lot of work on this, and you can see this paper is on regression analysis for interval value data. Now, I think it's interesting to think about X and Y. If they're both continuous random variables and we round them, then what we have instead of points, we really have little rectangles. And the point would fall right in the midpoint of the rectangle. But sometimes the rectangles are so large that we really can't ignore the fact that we have some uncertainty and that we really shouldn't just use the midpoints. So I did want to point out, make sure it's clear, there is a statistical area of research called interval statistics out there. Now, we also found this paper appeared about a dozen years ago, a resampling approach for interval value data regression that uses the same type of simulation that we're using, where you sample from the intervals. And I have an example. This is regression data. You can see that sometimes Y is interval valued, X1 and X2 are the explanatory variables. Sometimes they are interval valued. And we want to analyze this data. And we know that in statistics, whenever you have data, it's always good to look at plots. So if we plot the possible values here, Y versus X1, Y versus X2, you get these plots. So it shows you what the possible values are. And what we're going to be doing here is sampling one value from each of these regions. Now, if you look at this, I think it's important to ask yourself, how strong is the linear relationship? What value of R squared would you think would be reasonable with data that had this type of pattern? Hopefully some of you out there will chime in and give me a number. My own view is it looks like it's a pretty strong linear relationship. It turns out that X1 and X2 are correlated themselves, but if you just look at X2 and we're taking one value from each of these intervals, that's a pretty strong relationship. So our simulation showed that we very rarely got a value below 80%. And sometimes we got a value close to 100%. But if you look at the Neutrosophic interval, it goes from 10 to 20%. I mean, it's really kind of an absurd result. It's way, 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 way off here. And you would think that given this example, that if there was a reply to our paper, that they would address this example, or if they made a mistake in their calculations to fix things. But there isn't an effort to to do either one of those two things. So they, as I said, they always reply to our critiques. So here we have three papers: a critical evaluation of the criticisms against their methods. Um, I don't think, in my view, they didn't do a very good job here of addressing our points, and in some cases, they presented contradictory results. Um, Again, I'm happy to send you any of these. They didn't like our simulation framework. They didn't like the fact that we used a uniform distribution. Now, if you used any distribution for the data intervals that has support over the entire interval, any kind of beta type distribution, you're not going to affect at all the maximum and minimum values. You're just going to affect the distribution of values within the max and min. So they came up with a new simulation framework that honestly I think is incomprehensible. The key to ours is so simple. And I did want to point out that they had this paper in the Journal of Statistical Computation and Simulation, which is a good journal, but they let this paper get through. And again, it's not coherent. Their arguments are just simply not coherent. Um, I think it's important that we don't let Neutrosophic statistical methods enter into the mainstream of statistics because, as I pointed out, the methods are flawed and they don't address the obvious flaws as they come up. It doesn't give me confidence in really anything that they do. And because we feel like it's important for more statisticians to know what's going on in this area, because it is growing, Abdul and I've submitted this paper to the American Statistician. There hasn't been any kind of reply yet, but we summarized some examples similar to the ones that I presented here, but also we found some issues with their use of Neutrosophic arithmetic and their use of Neutrosophic random variables. If you have questions about this, I'm more than happy to answer them. I don't want to get into all the details, although it's very simple. Uh, uh, but the jury's still out on this paper. I hope that it will appear in the American Statistician. So conclusions, the simulation approach, I think, is very useful. If you do have interval data, then if you use the simulation approach, it doesn't require any kind of new theory. You're just putting the standard theory into a do loop, basically. And it's more informative than determining just the limits on the function, because the limits can be very wide, but the distributions can be concentrated away from the limits. So the limits don't provide nearly as much information as the distributions. So avoid using midpoints with chunky data. We recommend the simulation approach. Using just the two sets of interval endpoints to get Neutrosophic bounds is not meaningful. They can't say even what they're trying to capture in that interval. And our basic opinion is that their approach is fundamentally flawed, and I don't see any evidence that they're trying to fix any of it. I'm not sure that it can be fixed when it comes down to it. So that concludes my presentation. So I'll stop the share screen here.
Bill, thanks very much. Let's see, are we back working again here, guys? Okay, we're back. We're back in action again. Thank you very much for this talk. This is, I think, very informative, and one of the things that I kind of hope that people watching the Fireside Chat will take away from this is this is I've sort of view this as a beware type of talk, a warning to the unsuspected user, that you might be confronted by this sometime, and hopefully this will help you, uh, you know, evaluate the situation and come to an appropriate answer.
And but we do give an approach that will work if you have interval data
Yep.
in design experiments and you want to analyze it as interval data, then using the simulation approach, I think, is the way to go.
Absolutely, and it's the results are explainable, and it's all within the context of what I think of as classical methods. So I think that's the right idea. Um, I don't really totally understand the criticism of using a uniform distribution for the simulations. I don't really think it would make a great deal of difference if you used any other distribution over that interval.
Well, one way to look at it is that if you use a different distribution where the distributions have smaller variance than uniform, then the variance of your output is going to be less.
Yeah.
So it does have an effect. The distribution you use does have an effect on the distribution of your statistic, but it won't affect the maximum and minimum possible values
Mm-mm.
as long as you have support over every single interval.
Yeah.
I would point out that in their simulation approach, they start out using the uniform distribution, but they modify it, throw in a bunch of other uh, things that I really don't understand. But they end up with something that's not that much different from what we did, except it's just far, far, far harder to understand.
Well, that's one of the whole problems I think about this business of Neutrosophic statistics is that the writing about it is very unclear. It's difficult, and I've looked at this a lot, and it's difficult to understand exactly what they're doing and what they're trying to do.
But what I don't understand is why they didn't tell us several years ago how they were doing their calculations, because we've been asking how they do their calculations for quite some time. I thought they were using some kind of rule similar to what's in interval analysis, but
Mhm.
in many cases they aren't.
Well, an interval analysis, as I understand it, is a pretty well developed field. Uh, there's a lot of structure there that uh, seems to make some sense.
Interval analysis, I think, is a well-established field in numerical analysis,
Mhm.
but it does get very, very complicated. And we've seen a couple of papers where people tried to use it, and then our simulation results showed that they didn't get the right answer. The thing is, the simulation could be used to verify results. Could be used to verify the results that you might get from using interval analysis. And the simulation results could be used with any Neutrosophic example, but I would expect that every single one of them would show that they're not really capturing the full range of the statistic.
Yeah.
And again, they cannot say specifically what they're trying to capture in their interval. And if you can't say what you're trying to capture, then there's no way of really using it or evaluating it.
Well, I have always been a big proponent of Monte Carlo methods in general. And I think this is an ideal application for simulation where you do have uncertainty caused by rounding or by converting from one unit to another, from pounds to kilograms or whatever. I think the simulation approach is an ideal way to do that, and it's with modern computer software, should be relatively easy to do.
I think that's one of the keys is it is simple and requires no new theory at all.
Yeah. And you can use a software package. We've worked some with Caleb King from Jump SAS, and you can use a package like Jump and embed that inside your simulation pretty easily. In fact, you can do it all within the Jump scripting language. So it's something that uh, should be easy to implement. And to me, I like it because it's understandable.
Right, right. Well, I'm hoping that our involvement with Neutrosophic statistics is over now. I feel like that we've made our points and don't really have any more to say. I'm sure they're going to come back and say what they always say is we just don't understand Neutrosophic methods. But in a way, I guess they're right about that.
Yeah.
Uh,
There's certainly things that I have questions about, but I look at this as this sort of the same way that I look at some other sort of ideas that have grown up around the field of experimental design that ultimately we figured out were not the right way to do things. And the whole Taguchi controversy in the 1980s is a classic example of something else that sort of appeared to on the surface, and people got enthusiastic about it, and we started to see lots of papers appear on Taguchi methods, and it turns out that many of those ideas were flawed. And I personally think that we didn't react fast enough to point out some of the flaws and some of the problems. And it took people like Stu Hunter and George Box and a sort of a group of us in the experimental design area to kind of put down a lot of the things that Taguchi was talking about, like orthogonal arrays. Some of those were just really not good ideas, and signal to noise ratios for analyzing data. Just we eventually a lot of those ideas were shown to be not effective and not efficient, but it took a long time. And we in the experimental design community, we probably didn't react fast enough to that. And I'm hoping that this new stuff that we're seeing with Neutrosophic statistics, I hope that we're reacting fast enough to make sure that it doesn't get a serious foothold and lead to the same kind of confusions and controversy that went on during that Taguchi era.
right. I think that in some ways, Neutrosophic statistics and Neutrosophic methods is somewhat like fuzzy logic.
Yeah.
Became very popular at one time, and uh, we looked at a lot of fuzzy methods and really didn't see any value added. But I mean, that field is still out there. I mean, people are still publishing fuzzy logic papers. I get fuzzy logic papers submitted to quality engineering, and I'm sure you get papers submitted to QREI as well.
Bill, I had two fuzzy logic papers submitted this week.
Right, right. And fuzzy logic, fuzzy sets and systems is considered to be a statistical journal. And, I don't really want uh, Neutrosophic sets and systems to be put at that level.
Well,
I don't have anything personally against these guys, but
no,
in some ways they're like Taguchi in that even though Taguchi, they were valid criticisms, he never changed what he was saying. I mean,
yeah.
he always just kept saying the same thing. I think that uh, I
Well,
think you have to be willing to change.
well, I always told people, and I still to this day say that Taguchi should get a lot of credit because he got the problem right. The problem is how do you how do you deal with reducing variability through use of a designed experiment? How do you do that? That's an important problem, and we hadn't really thought about that much in the experimental design field until Taguchi comes along. So I think he should get a lot of credit for getting the problem right. Robust design, very important idea. And my whole quarrel is with the methods that he developed to try to do that. So I think that's you'd kind of hope that maybe something would come out of the this stuff that's going on with Neutrosophic statistics, and that people would realize that yes, there is a problem dealing with interval data, and the right way to do that is the simulation approach.
That's obviously what we think.
That's what I would hope would come out of this. But yeah, I get papers on fuzzy logic and fuzzy systems, and I wouldn't say I get a lot of them, but like I say, I got two this week. It's only Wednesday.
Well, I got one this week too. And I used to refer to our technometrics paper that we wrote on fuzzy logic, but I have sort of quit doing that and just say that the paper is outside the scope of the journal.
Yeah. Well, I remember a great comment that you made when we were sort of looking at all that fuzzy logic stuff. I remember you said fuzzy logic is for people that can't understand conditional probability.
My experience is that people that feel like that probability and statistics is not able to handle certain circumstances really means that the probability statistics that they understand is not able to deal with those. But I mean, probability and statistics can deal with a lot of different cases.
Yeah.
But we'll see how it develops. But one issue I think with these papers, so many papers being published, and again, none of them are reproducible, is I think a lot of it is flaws in the refereeing process, where if a editor of a journal gets a paper on Neutrosophic statistics, then chances are they're going to ask two people that have already published on Neutrosophic statistics to be the reviewers, and then so it just sort of continues on without a very critical look. I think that's one of the problems in the scientific literature is getting good reviewers can be a problem.
Now, the system that I use that for handling manuscripts for Quality and Reliability Engineering International, I can get a list of suggested reviewers, and there is an algorithm that the software uses to try to identify appropriate reviewers, and I actually get a percent score, as for each candidate that they give me that relates to what their background or knowledge or experience in the general area of that paper is. So do you get something similar like for that at Quality Engineering?
Quality Engineering, we get a list. I think it comes from the Web of Science. We get a list of potential referees. But if I have a paper on Neutrosophic statistics, chances are that list is going to contain people that publish on Neutrosophic statistics. So if I just go through there and pick my reviewers from that list, then I'm not going to get anybody that's really critical of the entire area. And our group, Doug, with you and Abdul, and Caleb, I don't know of anybody else that's even looked at any of this Neutrosophic statistics.
No, I don't either.
It's very, very difficult to understand their papers. I mean, they're tend to be not clearly written, and it's really difficult to follow. And We saw a couple of papers recently in Sankhya on Neutrosophic random variables, and uh, I don't want to go into the details, but basically they're reinventing the wheel, and some theoretical results there. So,
Hmm. And
uh,
that's a very respected journal.
well, I mean, at least it used to be. I don't think it's that highly ranked anymore, but I
Yeah,
always thought that Sankhya was a good journal.
I did too. I did too.
But that's one thing. If anybody's interested, we talk a little bit about the Neutrosophic random variables in the paper that we submitted to the American statistician.
Well, one of the things that I do with the list of reviewers that I get from my manuscript handling system is, in addition to, sort of a percent score, I also get information about have they reviewed for my journal before, and I tend to try to choose people that have served as a reviewer before more than once, and I've had pretty good success with that. The only problem is I think I'm wearing out friends. I'm abusing people by sending them too many papers to review, and because we get a lot of submissions. I don't know how many submissions you get, but we get a lot. I
Yeah,
had I
you
had
get a
I
lot
had
more than we do.
I had 40 yesterday.
Oh my gosh.
Yeah, when I did not look at anything on Monday, but when I turned my system, my email on Tuesday, I found 40 new papers that I was invited to handle, and my co-editors, Arnott and Elsie Tank, they get about the same number. We get a huge
Well, it is a problem, and there are a lot of problems in the scientific literature now with AI and a lot of misbehavior. So I recommend that anybody is interested in sort of the misbehavior in academic publishing, look at retractionwatch.com.
yeah.
They have plenty of examples there. And I have a presentation that I've given several times just on the ways people are gaming the publication and citation processes. I mean, I had one author submit a paper to quality engineering that contained over 70 self citations. Uh,
Wow.
and it wasn't a review paper, it was a short mathematical paper.
Oh,
So, and that wasn't the only paper this person submitted with that many self citations. People are trying to game the system these days.
well, you brought up the topic of fraud in scientific publications. Something that I encountered, and a book that I've read, and I've recommended this book to lots of people. The name of the book is called Doctored. Okay. And it's written by an individual who is one of the editors of Science, Nature's, publications. And what he's pointing out is the amount of scientific fraud that has gone on in the research literature on Alzheimer's disease. And I'm astounded. Uh, People are publishing articles with fake images of brain scans or of protein materials from the brain. They're publishing articles with data that has clearly been doctored, so to speak, in some way. And
He
and
recommended that book to me, and I read it. And the disturbing thing about that book is that the images were manipulated by reputable scientists.
yes,
I mean, it wasn't people buying papers from paper mills and things like that. It was reputable scientists that wanted to make a particular point, but they could make their point stronger if they manipulated an image somehow.
hmm
And it
yeah,
seemed like virtually everybody in that field was manipulating images. So, and that's going to be a bigger problem with AI because you can get AI generated images that are much harder to detect
Right.
manipulation. It's that's another issue of what's happening here. I think other fields are affected more than statistical field by all this misbehavior, but we still have uh, our share of it. Uh, but the medical literature has really been hard hit
Yeah.
with fake papers uh, and people making up data. And the way that most of the people are discovered for making up data is they don't put enough variation into their data.
Bill,
I mean, that
that's
goes all
been
the way
my
back.
experience. That has been my experience.
uh,
People don't understand variability, and they when they make up the data, it's too good.
right, right. And that's usually how it gets discovered. And
Yeah.
then once one paper has been identified, um, with fake data, then every other paper that person has published gets put under a microscope. And there are people out there that have had hundreds of papers retracted
Yeah.
uh, because of things like that. So I think it's a big issue with the scientific literature now. And again, I got involved in that area through Taylor and Francis, who publishes quality engineering. But
Mhm.
I've done quite a bit of studying of different ways that people are gaming the system.
Well, the first time that I really realized this topic we're talking about was not with journal papers, but was an intellectual property lawsuit. I've had the good fortune, or I should say the maybe sometimes the lack of good fortune, to be retained by attorneys in intellectual property law, and it's really interesting because a lot of times these cases do boil down to looking at data, because that's often how you see that there maybe have been some sort of patent infringement. And I remember the one case that drove this home to me is that we were looking at uh, a property of a chemical product, and it just looked really too good to me. It was just no variability much, and I did not, I don't pretend to be a polymer chemist, and so I told the lawyers that you should have somebody who is really truly an expert in polymer chemistry, look at this data because I'm suspicious just purely based on the fact that it doesn't vary very much. And so they went out and they found a guy that wrote the textbook on polymer chemistry, okay, world authority. And he came in and he looked at the data, and I'm sitting there with him, and the lawyers are there. He spends 30 seconds looking at the data, and he says, "This is all made up." He said, "There is no way you could get this level of precision in this quantity," and said, "We can't even measure it to this level of precision using like a gel permeation chromatograph." And that led me to believe that, and this is years ago, Bill. This is back in the 80s. And it led me to believe that what you said is exactly correct, that when people make up data, they make it up too good.
Right, and I think one problem is that the expectations for publishing are so high
Yeah.
across the entire world, and um, we have journals that will publish practically anything because the authors have to pay $2,000 or $3,000 to get their paper
Yeah.
published.
Yeah.
So if you were going to send me a paper and I was going to decide where to publish it and whether or not you sent me $3,000 was in the up for grabs here, I'm going to lower my standards. Instead
Yeah.
of is this paper good enough to be in my journal, it's more like will this paper embarrass me if I publish it in my journal?
Yeah. And
So there are a lot of
can
pay
they
to
pay
play journals out there.
and can they pay the fee? Yeah, I think the rise of these pay to play journals is have been a problem. Bill, we're getting close to the end here. The Our production team is telling me to shut up. So we
Okay, well,
have
again,
to.
I appreciate the opportunity, and anybody that wants copies of papers, I'm more than happy to send them.
Great. And I think this, I hope this talk does a lot to sort of forestall the rise of these methods in the experimental design world. To me, this is the same sort of thing, issue that we faced with the Taguchi controversy back in the 80s, and I'd like to get ahead of it. Our next fireside chat, by the way, is going to be on March 18. More information about that will be posted in Coursera. And a reminder that you can find past recordings on the resources tab in Coursera. And I'm looking forward to seeing folks again next month. And Bill, once again, thank you so much for taking time out of your day and ignoring Mardi Gras and all that fun stuff that's going on in New Orleans to.
Hey, Mardi Gras was over yesterday, so
Oh, okay. All right. Okay. Thank you again. I
all right.
appreciate this.